Have you ever wondered what might happen if a black hole started to vanish? The universe is a vast, seemingly infinite expanse filled with wonders and mysteries that continuously baffle and intrigue us. Among these celestial enigmas, black holes stand out as particularly fascinating. Black holes, these cosmic phenomena, are regions of space where gravity is so strong that nothing, absolutely nothing, can escape their pull. Not even light, the fastest thing in the universe, can break free from their gravitational grip. Imagine an astronomical object with such immense power that it can bend space and time itself. That's the might of a black hole. Yet as fearsome and powerful as they are, black holes aren't the invincible cosmic devourers we once thought. Paradoxically, despite their gravitational might, they might be slowly but surely evaporating. Hard to believe, isn't it? An object with such an insatiable appetite, so potent that it can swallow stars whole, slowly fading away into nothingness. This idea of black hole evaporation is not just a wild science fiction concept. It's rooted in the complex and often counterintuitive realm of quantum physics. The world of the incredibly small, where particles can be in multiple places at once and where the act of observing can change the outcome. In this realm, even black holes, with all their gravitational might, aren't immune to the strange and often bewildering rules of quantum mechanics. In fact, these rules may hold the key to understanding what seems to be an impossible paradox, how something as powerful as a black hole can slowly start to vanish. So are black holes really evaporating? And if so, how does this happen? What are the processes, the theories that could explain this seemingly impossible phenomenon? As we journey through the cosmos, let's unravel these questions piece by piece. Let's delve into the mystery of black hole evaporation. Stephen Hawking, a name synonymous with black holes, proposed a fascinating theory. He suggests that black holes, those mysterious cosmic entities, are not just vacuum cleaners of the universe, but they also emit particles. Yes, you heard it right. Black holes are not just eternal prisons from which nothing escapes. They actually emit particles, a phenomenon we now know as Hawking radiation. Now, let's delve a little deeper. You see, the universe at the quantum level is a busy place. It's filled with particles popping in and out of existence. These particles, known as virtual particles, usually annihilate each other almost immediately, but something extraordinary happens at the edge of a black hole, the event horizon. Here, a pair of virtual particles can be separated by the black hole's immense gravity before they have a chance to annihilate each other. One particle falls into the black hole while the other escapes into space. To an outside observer, it appears as though the black hole has just emitted a particle, hence the term Hawking radiation. So what does this mean for the black hole itself? Well, energy can't be created or destroyed, it can only change forms, right? That's one of the fundamental principles of physics. When the black hole emits a particle, it loses a tiny bit of its energy and therefore its mass. Over incredibly long periods, this process can lead to the black hole losing significant amounts of mass, causing it to shrink and ultimately evaporate completely. This is a slow process. A black hole with the mass of our sun, for example, would take longer than the current age of the universe to fully evaporate. But for smaller black holes, the process could be much quicker, potentially leading to a final dramatic explosion. So, in a sense, Hawking's theory turns the traditional view of black holes on its head. They aren't eternal, unchanging objects, but evolving entities that can grow and shrink and potentially even die out completely. But the question remains, how does this evaporation occur? Let's explore that next. Welcome to the world of quantum physics, where particles can do the impossible. In this realm, we encounter a phenomenon known as quantum tunneling. You see, the quantum world doesn't play by the same rules as our everyday reality. Particles can seemingly teleport through barriers, an event that would be impossible in classical physics. One such barrier is the event horizon of a black hole, a boundary beyond which nothing, not even light, can escape. Yet quantum tunneling suggests that particles could, in fact, escape this seemingly insurmountable barrier. How? Well, due to the inherent uncertainty in quantum mechanics, there's a slim chance that a particle could be on one side of the barrier one moment and on the other the next. This quantum leap could allow particles to escape the black hole's grasp, contributing to its slow but steady evaporation. Fascinating, isn't it? Yet this is only one piece of the puzzle. In the quantum realm, reality is stranger than fiction. This is a world where particles can be in two places at once, where they can pop into and out of existence seemingly from nowhere. Here lies our next piece of the black hole puzzle, the concept of virtual particles. Virtual particles are a peculiar feature of quantum physics. Think of them as temporary, ghost-like particles that borrow energy from the universe for a fleeting moment, only to vanish as quickly as they appeared. They are part of the quantum foam, the seething cauldron of activity that is the fabric of space-time at its smallest scales. But how do these virtual particles relate to black holes? To answer that, let's visit the edge of a black hole, the event horizon. Here, the gravitational pull is so intense that even light cannot escape its clutches. Yet, this is also where virtual particles play their most dramatic role. In the vicinity of a black hole, a pair of virtual particles, one matter, the other antimatter, can pop into existence. Now, typically, these pairs annihilate each other almost immediately, disappearing back into the vacuum. However, if they materialize near the event horizon, something remarkable can happen. One particle might fall into the black hole while the other escapes into space. If the escaping particle is the matter one, it adds a tiny bit of energy to the universe. But to balance the books, the black hole must lose an equivalent amount of energy, or in other words, mass. This is essentially the process of black hole evaporation, as first proposed by Stephen Hawking. In this way, virtual particles could be slowly eating away at black holes, borrowing energy from them and then disappearing, leaving the black hole just a smidgen lighter. This process is incredibly slow for large black holes, but over astronomical timescales, even they could eventually evaporate completely. So, could these virtual particles be the key to black hole evaporation? As with many things in quantum physics, the answer is both complex and fascinating. But one thing's for sure, in the quantum realm, reality is indeed stranger than fiction. Imagine a world where you could have less than nothing. Sounds impossible, right? But in the quirky realm of quantum physics, this is a reality, and it's called negative energy. Now, don't think of it as an energy that's in a bad mood, but rather energy that's less than zero. Negative energy plays a crucial role in the evaporation of black holes. Picture this, a pair of virtual particles, one with positive energy, the other with negative energy, popping into existence near the event horizon of a black hole. The positive energy particle escapes while the negative energy particle falls into the black hole. This process decreases the mass of the black hole, essentially causing it to shrink or evaporate. In this way, negative energy could be used to balance the energy books when virtual particles escape, helping us understand the enigmatic phenomenon of black hole evaporation. But what if there were other factors at play? Or what if I told you that two particles could be instantly connected, no matter their distance apart? This isn't the premise for a science fiction novel, but the real mind-bending theory of quantum entanglement. It's a phenomenon that Albert Einstein famously referred to as spooky action at a distance. And it's one of the most intriguing concepts in quantum physics. Quantum entanglement occurs when two or more particles become linked, and the state of one immediately influences the state of the other, regardless of how far apart they are. It's like having a pair of dice that, no matter how far you throw them, always land on matching numbers. But how does this relate to black holes and their evaporation? Well, the theory suggests that quantum entanglement could play a key role. You see, when a particle-antiparticle pair is created near the event horizon of a black hole, one might fall into the black hole while the other escapes into space. If these particles are entangled, the fate of the one inside the black hole could influence the one that got away. Some theorists suggest that the information about the particle that fell into the black hole isn't lost, but rather it's encoded in the state of the escaping particle. This concept, known as the holographic principle, could explain how information escapes from black holes, contributing to their evaporation. However, this theory isn't without its controversies. The idea that information can escape from black holes contradicts the traditional view that nothing can escape a black hole's gravitational pull. This paradox, known as the black hole information paradox, is one of the greatest unsolved problems in theoretical physics. So quantum entanglement presents a fascinating possibility. It suggests a universe far stranger and more interconnected than we could have ever imagined. A universe where particles across vast distances are linked, where information might escape the inescapable, and where black holes might slowly evaporate over eons. Could this spooky action at a distance be the answer we're looking for? The mystery continues to unravel as our understanding of the quantum world deepens. Beneath the surface of space-time, things get a bit frothy. Welcome to the realm of quantum foam, where the universe is a seething, bubbling cauldron of tiny, transient phenomena. This is the world of quantum mechanics, the scale where the fundamental particles of the universe reside, and the laws of physics as we know them start to twist and turn in unexpected ways. Quantum foam is a concept proposed by John Wheeler, a physicist known for his work in quantum gravity. According to Wheeler, at scales smaller than what's known as the Planck length, space-time itself becomes volatile, fluctuating wildly and giving rise to fleeting particles and antiparticles. Picture it as a sea of bubbles, each one popping in and out of existence in the blink of an eye. But what has this got to do with black holes? Well, these fluctuations could play a role in the evaporation of black holes. You see, when these particle-antiparticle pairs form, they usually annihilate each other almost immediately. However, if this happens at the event horizon of a black hole, one of the pair could fall in before the annihilation happens, leaving the other without a partner. This lone particle can then escape into the universe as Hawking radiation, a process which takes a tiny bit of energy and therefore mass from the black hole. Over unimaginably long periods of time, this process could cause the black hole to lose enough mass that it effectively evaporates away. But this is all theoretical. The scales we're talking about are so small and the energies involved so immense that we currently have no way of directly observing or testing this. Quantum foam remains a fascinating yet unproven concept in our understanding of the universe, and yet, as we delve deeper into the quantum world, we can't help but wonder, if the universe is full of this frothy, fluctuating foam, and if these tiny bubbles can have such a huge impact on something as massive as a black hole, what else might be influenced by these quantum fluctuations? But could there be a larger cosmic process at work? The exploration of quantum foam continues, opening doors to even more intriguing questions about our universe. Let's venture beyond our universe and into the realm of the cosmological constant. Now, what is this cosmological constant we speak of? It's a concept introduced by none other than Albert Einstein as part of his theory of general relativity. He proposed it as a way to balance the gravitational pull of matter and ensure a static universe. However, ironically, this constant might be the reason why our universe is expanding, not static. Think of the cosmological constant as a sort of anti-gravity. It's a mysterious energy, often referred to as dark energy, that permeates all of space and pushes galaxies apart. The more space there is, the more this energy can do its work. It's like a balloon inflating. The more it inflates, the faster it inflates. So, how does this relate to black holes? Well, as the universe expands, the distance between galaxies, stars, and yes, black holes increases. The density of matter in the universe decreases. This expansion could have significant implications for black holes. Black holes are, by definition, regions of space where gravity is so strong that nothing, not even light, can escape. But what happens when the universe itself is stretching, becoming less dense, and the gravitational pull of these black holes becomes weaker? What happens when the cosmological constant, this dark energy, starts to overpower the gravitational force of black holes? Some scientists speculate that as the universe expands, black holes might slowly lose their grip on the space around them. The event horizon, the point of no return around a black hole, might start to shrink. Over unimaginably long timescales, black holes might slowly evaporate, their mass carried away by the expanding universe. This is just a theory, of course, and much more research needs to be done. But it's a fascinating concept, isn't it? That the very fabric of our universe, the constant expansion driven by this mysterious dark energy, could be the key to understanding the fate of black holes. So could the fate of black holes be tied to the fate of our universe? Could the universe end not with a whimper, but with a rip? Enter the Big Rip theory. This mind-boggling concept postulates that the accelerating expansion of the universe could eventually become so powerful it might literally tear everything apart. Yes, you heard that right. Everything, from galaxies, stars, planets, to even the smallest particles. So where do black holes fit in this cataclysmic scenario? Well, according to the Big Rip theory, not even the immense gravitational pull of black holes can withstand the relentless, ever-increasing expansion of the universe. As the universe expands, black holes too would be stretched out, causing them to lose their mass over time. This stretching could lead to the evaporation of black holes, leaving absolutely nothing in their wake. It's a chilling thought, isn't it? An end where everything, including the enigmatic black holes, just disappear. But remember, these are all just theories. The true nature of black holes continues to elude us. Black holes, these enigmatic giants, continue to baffle us. We've journeyed through an array of theories, each one as fascinating as the last. Each one a testament to the relentless curiosity of human minds. Yet we find ourselves standing at the edge of the cosmic abyss, gazing into the unknown, realizing that our understanding is still in its infancy. We began with the enigma of black holes, these cosmic vacuum cleaners, swallowing everything that dares to cross their event horizon. Then we dived into the theory of Hawking radiation, a concept that suggests black holes aren't as eternal as we once thought, that they might be slowly evaporating, losing mass over time due to quantum effects. We explored the idea of quantum tunneling, a process that might allow particles to escape from the clutches of a black hole. We delved into the realm of virtual particles, pairs of particles and antiparticles that pop in and out of existence in the vacuum of space, potentially playing a role in black hole evaporation. We contemplated the concept of negative energy, a phenomenon that could cause a black hole to shrink over time. We pondered over quantum entanglement, a strange aspect of quantum mechanics that might explain how information escapes from black holes. We considered the idea of quantum foam, the fabric of space-time at its smallest scales, possibly playing a role in black hole evaporation. We reflected on the cosmological constant, a mysterious value that might influence the rate of black hole evaporation. And we ended with the Big Rip, a hypothesis that suggests the universe itself might tear apart, taking black holes with it. Yet despite all these theories, despite all our intellectual endeavors, the mystery continues. Each answer we find only leads to more questions, more puzzles to solve. As we continue to gaze into the cosmos, the mystery of black hole evaporation remains, waiting to be unraveled by the minds of curious scientists. As we perch on the precipice of this cosmic chasm, we extend an invitation for you to accompany us on this quest for knowledge. The universe, a vast expanse laden with conundrums and enigmas, beckons us. Black holes, quantum entanglement, virtual particles, and more. There's an uncharted terrain awaiting our exploration and comprehension. Thrilled that you're here with us, a part of this awe-inspiring journey. If this deep dive into the universe's secrets has enlightened you, we'd appreciate your feedback. Which caught your attention? What topics would you like us to delve into more? Comment below and share your thoughts. Your ideas and inquisitiveness are the driving force behind this journey. If you haven't done so already, please consider subscribing to our channel and hit the bell icon for more such enlightening content. We're on a perpetual journey of exploration and learning, and it would be an honor to have you accompany us. Lastly, if you know someone who is as captivated by the cosmos as we are, share this video with them. Let's proliferate the sense of wonder, curiosity, and joy of discovery, because the universe is too boundless, too stunning, and too intriguing to explore alone. So let's persist this cosmic expedition together, unraveling mystery at a time. If you've learned something new from this video, don't forget to give it a like. And please, share your opinions and thoughts in the comments section, and don't forget to subscribe. Press the bell icon for more such content, and do share it with your friends and family. Extend the knowledge, extend the joy.